This video contains solutions to some of the homework problems from Chapter 8, numbers 17, 19, 21, and 25. Copied the diagram for number 17 down here. So we're releasing a block from up here, a block with a mass of with this mass here, and it's going to go around this loop, or hopefully go around the loop. We'll see. And the first part is, what is the magnitude of the horizontal and vertical component of the net force acting on the block at point Q, which I believe is right here. And the block is right here. So I think first of all, what forces are acting on the block there? And there are two. There's going to be a normal force. It's up against the edge of the ramp here. So there will be a normal force perpendicular to that ramp. And there will also be a gravitational force. The gravitational force is just mg. So I think that's the answer to part B right there. B is the magnitude of the vertical component is just mg. So you can calculate that, 0.032 times 9.8. The normal force, that's a little trickier to figure out. If you're not convinced that there would be normal force, this thing's going to have a good bit of velocity when it gets to this point, right? And we can figure that out in a second using energy conservation. And if it's moving in a circular path, then it can't move in that circular path unless there is unbalanced force toward the center of that circle. And that unbalanced force toward the center of the circle is coming from the normal force. So the normal force is equal to the centripetal force. Or maybe it would be more instructive to say that the normal force is providing the centripetal force, right? This is not a force unto itself. It's just how we describe the unbalanced force towards the center of the circle. So where's the centripetal force coming from? It's coming from the normal force. So if we can figure this out, that will be the magnitude of the normal force. So to figure out how fast it's going here, we just have to do energy conservation. So we know the total energy in the system is constant because there are no non-conservative forces. So that means at the top, it's not moving yet. So mgh at the top is equal to mgh at point Q plus 1/2 mv squared at point Q. Notice that there's an m in all of these, so that doesn't actually matter. So I have g times the height at the top is 0.6 be equal to g times the height at point Q, which would be 0.12, plus 1/2 is the velocity q squared, and I'll do a little bit of calculator work here, figure that out. And we have, let's see, that's going to be a 0.48 times 9.8 when I move that over to the other side. And then I'm going to have to divide by 1/2, which is, or multiply by 2 in other words, and then take the square root of that. So the velocity at point Q will be 3.07 meters per second. And then the normal force is going to be mv squared over r. I have the v squared there, so I'll take that. So the mass, where'd that go? 0.032 times the velocity squared, which is 9.41, say, divided by the radius of the circle, which is 0.12. So there's about 2.5 newtons of normal force. That's the answer to part A. And then that's the answer to part B. Part C would like us to figure out at what height h should the block be released from rest so that it is on the verge of losing contact from the track at the top of the loop. So that's when the normal force is 0 there, and they give us that hint there in the book. So here that would mean that at that point the normal force would be 0. Now that means if the normal force is 0, the only force acting on the block at that point is mg. And that is pointing directly toward the center of the circle. So at that point, when the normal force is backed off to 0, it would mean that the gravitational force is supplying that necessary centripetal force, which is mv squared over r. So mg is going to be equal to mv squared over r. The m's cancel, so v will be equal to the square root of gr. So let's see what that is. That's square root of gr. So that would be 1.08 meters per second. That's the slowest the block can be going and still make it through the loop. Any slower than that, what would that mean? That would mean this number would be smaller, but you can't reduce the amount of gravity. So that would mean we would have more force toward the center of the circle than the necessary centripetal force for that velocity. In other words, it'll get pulled out of the circle. Get pulled out of the circle by too much force toward the center of the circle. Right. So if we want to have a velocity of 1.08 meters per second at the top of the loop, then where do we have to release it from to make that happen? So we could do an energy conservation equation just like this one. So if mgh from I don't know where would be, there are different ways you can subscript that, and it's kind of awkward, but I'm trying to figure out that height, right? Would be equal to mg times the h at the top of the loop plus 1/2 m v squared, where this is our v, right? Our minimum velocity to make it through the loop. So the m's all cancel out. We get the h that we're looking for here is equal to 9.8 times the height at the top of the loop, which is 0.24, plus 1/2 times this velocity squared all over g, dividing by that g there. And let's run that through, see what we get. 9.8 times 0.24 plus 0.5 times 1.08 squared, all divided by 9.8. We get height of 0.405. That's where you would have to release it. And I'm a little bit skeptical of that answer. Yeah, that's not right. So somewhere I've made an error here, because I happen to remember from past problems, from doing this before, that if you do this without an actual r in this problem, there is a generic answer for this, that if you want to release a block and have, or some kind of mass, and go through a frictionless loop, you have to release it from 2.5 times the radius. So somewhere I've made a mistake here. Let's see if I can just figure out where that is real quick. So we went square root of gr. That's right. And then that's the height at the top of, oh, wait a minute. No. No, that's right. Let me just try to run through that again. 0.8 times 0.24. Maybe you already know where the mistake is. Maybe you saw it. Times 1.08 squared. I'm going to divide that all by 9.8. Oh, there we go. So I don't know what I did before, but this is set up right. So, and that's 30 centimeters. And notice that that is 2.5 times. You can run that whole calculation without knowing anything, and you would find that the height that you have to release it from is 2.5 times the radius. Right. Now part D, they want to know what would a graph of normal force on the block at the top of the loop versus where you release it from. Here's R, 2R, 3R, and so on. Well, if you release it from R, like here, it's only going to go, it can't go higher than this, right? So it's never going to make it to the top of the loop. You release it from here, it won't have enough velocity, it'll fall out of the loop. And what we just showed here is that 2.5 R, that's the place where you get zero normal force. And then from there, it increases. And I'm going to leave it to you if you want to pursue this further, if you're interested, to show that in fact that would be linear. It's not that hard to do. You just have to either, there's a couple ways of doing it, to find that function of normal force, in other words, find the centripetal force as a function of the height that you release it from. And it does turn out to be a linear function. So, or you could just try it for some other values and plot them. But that's a little bit beyond what I think I want to do here. So I'll leave that to you if you're interested. I think that what I'm most interested that you get from this is that there would be no normal force here because it doesn't even make it to the top of the loop. Here is where it would be zero, and then it would definitely increase as you release it from higher and higher in the loop. Well, that was a long problem. All right, 19. So we can make quicker work of that. In 19, we have an 8 kilogram stone that's at rest on a spring. Here's the stone. It's at rest on a spring. And the spring is compressed 10 centimeters by the stone. So let's just find the spring constant. So when it's at rest, then we know that the gravitational force is balanced by the spring force. And I'm just going to deal with the magnitudes here. I'm going to ditch the negative sign on that because I'm just matching up the magnitudes. So the mass of the stone is 8 kilograms times 9.8 is equal to K times X, which is 10 centimeters. Just watch your units there. And that will give me 8 times 9.8 divided by 0.1, 784 newtons per meter. Part B, the stone is pushed down an additional 30 centimeters and then released. What's the elastic potential energy of the compressed spring just before that release? Well, at that point, it's been compressed a total of 40 centimeters. So the energy stored in the spring is 1/2 kx squared, and that's 1/2 times k times the total compression. It was already compressed by 10 centimeters, so an additional 30, and give us 40 centimeters total. So that's 1/2 k times x squared. So that's about 63 joules of energy there, or 62.7, something like that. In part C, what's the change in gravitational potential energy of the stone-earth system when the stone moves from the release point to its maximum height? So we're going to release it from here, and we want to know what's the total change in the gravitational potential energy. Well, if you think about what's happening, we have this spring compressed with the rock on it, and then it's going to go up into the air, and at some point it'll reach its maximum height here. At this point here, all of the energy in the system is in the spring. At this point here, all of the energy is gravitational potential energy. And we know how much spring energy there is here. So this is the size of the pie, right? This is the power of energy conservation. If we know the energy at the total energy at any point in the system, that's the total energy anywhere. So at the very top, we know it's all gravitational potential. At the very top, it's not moving, and the spring has done the spring has sprung. So that means that the change in gravitational potential energy will be 63 joules. It will gain that much potential energy. And then what's the maximum height from the release point? Well, this is mgh, so 63 to 8 times 9.8 times that maximum height. So the book used 60.7, so I'll do the same thing, divided by 8 divided by 9.8. So about 80 centimeters. There you go. That was easier than 17. Alright, let's see how we do with number 20. Is it 21 the next one? Or we're skipping. 21 is the next one. And 25. Number 21, figure 832, it's on the previous page. It shows a pendulum of length 1.25 meters. Its bob, which effectively has all the mass, in other words, we're ignoring the mass of the string, has a speed v sub 0 when the cord makes an angle of 40 degrees with the horizontal. With the vertical. So that's 40 degrees there. What's the speed of the pendulum when it's at its lowest position if v sub 0 is 8 meters per second? So that's an energy conservation problem. We have to do a little bit of trigonometry here to figure out what this change in height is right here. That's going to be important for us, right? Because it's got some gravitational potential energy here. How much does it have? It's got that much worth, right? So let's do the trig. This right here would be the cosine component of this. So I'm in degree mode, groovy. So 1.25 times the cosine of 40 gives me that this is right here at 0.96 meters. And that means that this is 0.29 meters, because I have to add up to 1.25. So that's the change in height. That's what I need to do this first part. Right, so part A, my energy conservation equation, at the top here we have gravitational potential energy and kinetic energy. It's moving. The bottom, that's our 0 point for gravitational potential, so it's gone as low as it's going to go, and there it's all just kinetic at the bottom. So this would be mgh plus 1/2 mv squared is equal to 1/2 m velocity at the bottom squared. The m's cancel out, as they often do. So let's see what we got here. I've got 9.8 times 0.29 plus 1/2 times 8 squared. That's that side. Then I have to multiply by 2, and then I need to take the square root of that. And that gives me, it has a velocity at the bottom of 8.35 meters per second. Not a whole lot faster than it was going. Part B. What is the least value that v sub 0 can have if the pendulum is to swing down and then up to a horizontal position? So, if it's going to make it to a horizontal position, let me redraw. So to make it to a horizontal position, I know that here at this position it had a velocity, where we want to know how much velocity does it have to have here to make it up to here. Well, this distance, the difference, in height here is 0.96 meters. So I have to go from having kinetic energy to 0.96 more of potential energy. So 1/2 m v sub 0 squared would have to equal mg, and then it's going to go up by 0.96. If you set this up with an equation that looked more like this on the left side, you can do that, but it's going to reduce to this because what really matters is the change in height, right? If you've got mgh's on both sides, when you subtract one over, you're going to get that same thing. So if you set it up like that, that's fine. Mass cancels. So how fast would it have to be going to make it to the horizontal? It would have to be, let's see, the square root of 2 times 9.8 times 0.96, which is 4.34 meters per second. And part C. Now we want it to make it to a vertical position with the cord remaining straight. So that means the tension would just it's kind of like the loop problem. That means the tension is just barely going to back off to 0 at that point. If you feel like that's worth talking about some more, think about the loop-to-loop problem. We need, the cord will remain straight as long as there's any tension at all. So if it can make it to the top just with the tension backing off to 0, then the cord will remain straight and it'll start to get tight again as soon as it passes that top position. This is very, very much like the loop-to-loop problem. So if the tension is backed off to 0, then that means the centripetal force will have to be equal to mg. So mv squared over r is equal to mg. And once again, we find that expression that the velocity required for it to barely make it through its circle with its string remaining straight is the square root of gr. So we can calculate that if we want to, or we could just leave it as that, I suppose, too. I'll go ahead and calculate it. So we have the square root of g times r, and the radius of the circle is the length of the string. That's 3.5 meters per second. So now we just have to do the same problem that we did here, but it's got to get from this position where it's 0.96 meters below the center of the circle, right? That's where it's starting off. And now it's got to make it all the way to the top of the circle, which is 0.96 plus a whole nother radius of the circle higher up. So that's going to look just like what I did in part B, except we're going to have 1/2 mv sub 0 that I don't know yet, and it's going to have to make it to the top where it will have mgh at the top's worth of potential energy plus 1/2 mv, the minimum velocity to make it through the circle, which we just found right there. So let's run that, see what we can do. The m's cancel out. So got v sub 0 squared is equal to 2 times g. The h at the top is the sum of those two, which will be, oh dear, what is that, 2.21? I hope that's right. Plus 1/2 times that minimum velocity that we just found squared. All right, let's crank that out. So we got the square root of 2 times 9.8 times 2.21 plus 1/2 times 3.5 squared. So that velocity at the bottom will have to be 7.45 meters per second to make it up to the top with the string just barely remaining straight. Cool. And part D, do the answers to B and C increase, decrease, or remain the same if the theta is increased by a few degrees? Well, if you increased the theta, then it would be starting at a little bit higher position, right? If it started at a little bit higher position, then it wouldn't need to gain as much here, right? So that means the velocity, that would mean this side of the equation would be a little bit smaller, right? This wouldn't be as big as 0.96 anymore. If we increase the angle, it's going to bring it up a little bit. So that would make this a little bit smaller. And likewise here, it would make it a little bit smaller, right? Because it would decrease that height at the top. So both of them would decrease a little bit. Go try it if you want, if you got nothing else to do. All right, last one. 25. Good thing you only get 4 problems at a time in physics, huh? So let's see. At time 0, a 1 kilogram ball is thrown from a tall tower with a velocity of 18I plus 24J meters per second. And they want to know what's the change in the potential energy of the ball-Earth system between time 0 and time 6 when it's still in free fall. So in other words, we've thrown it from high enough that it's still in free fall. Well, thinking back to our projectile motion days, this is just a ball that's been projected with a horizontal velocity of this and a vertical velocity of this. And if we're only interested in, let's say here's the ball, its initial velocity, it's going to follow a path like this, right? If we're only interested in the change in potential energy, we're only interested in the change in height. So we're only interested in the vertical part of this problem. The horizontal part doesn't matter. If the ball went from here to here, the change would be 0 in the gravitational potential energy. It only matters how high up it is from the surface of the Earth. So I'm going to ignore this completely, right? I only care about this. So I just want to know, where is it at? What's the delta y after 6 seconds? So here's the initial vertical velocity, right? The acceleration would be negative 9.8 meters per second, and the time is 6 seconds. And I would like to know what is the delta y. So I'm going to use the equation delta y is equal to 1/2 at squared plus vi t. So 1/2 is negative 9.8, because I chose up to be the positive direction, times t squared plus vi t. That will tell me the delta y, which is exactly what we need to know. So 0.5 times 9.8 negative, times squared 36, and I'm just going to go, I'll just say times -1, because I forgot the negative sign there, plus 24 times 6. So negative 32.4 meters. So what's the change in gravitational potential energy? Well, it lost this much. If we started here, it dropped 32.4 meters. So the change in gravitational potential energy is equal to mg times the change in its height. And that's the mass, I believe, was 1 kilogram times g times the change in height, which is negative 32.4. You're going to get a negative delta, as we know it's losing gravitational potential energy. That's what that means. So that number times 9.8. So we lost 317, or say 318 joules of gravitational potential energy.